So far we have learned how to write supersymmetric Lagrangians. Now today we have learned how to write supersymmetric Lagrangians for gauge theories coupled with matter of any kind, non-abelian gauge theories, abelian gauge theories, non-abelian gauge theories. So in principle we can write Lagrangian density now for any model we want. We want a supersymmetrized standard model. All we have to do is, for every gauge field you pick up a gauge group, you pick up a gauge multiplet, and for every matter particle of the standard model you pick up a chiral superfield and couple them through the constructions that we have set up. Today we are going to discuss supersymmetry breaking. Now supersymmetry cannot be an exact invariance in nature. So supersymmetry breaking. SUSY cannot be an exact symmetry. And the reason is obvious. If it were, then we would have already seen a superpartner of an electron, a scalar with the same mass and same charge. And we don't have any in nature. So supersymmetry should be broken. Now breaking a symmetry is nothing new to us, because in standard model of particle physics, we break symmetry. If we had not done that, then the weak gauge bosons W and Z would be masses like a photon. So we break it because nature wants them to be massive. So symmetry breaking is not new to us. So supersymmetry, for the same reason, will have to be broken. Now, but why do we believe that supersymmetry should be a property of nature? We believe supersymmetry should be a property of nature because supersymmetry theories have some nice properties. One of the most important properties it has is that quantum SUSY theories do not have quadratic divergences. So in a quantum supersymmetric theory, if you were calculated loop corrections, you would discover that generically in a quantum field theory, loop corrections are divergent. Some of them are quadratically divergent, some of them are logarithmically divergent. In supersymmetric theories, generically, there are some exceptions, we may make a mention there somewhere. Generically, quadratic divergences are absent. And if quadratic divergence is absent, then such theories have nice properties. And the nice property they have is then there is a distinction of the low and heavy mass scales in the theory is maintained under quantum perturbation, which is not the property of the standard model. Standard model with an elementary scalar Higgs, that's what we have discovered now, in nature does not have that property. So the standard model cannot be a complete description of nature. And if it's supersymmetrized, then the low scale mass, which is mass of W or mass of Higgs, would be stable, which means it will not receive any large radiative corrections. So that is the property. And that's the reason we want supersymmetry. But if you break supersymmetry, do you lose that property or not? Because we don't want to lose that property, because that was the only reason why we wanted supersymmetry. So supersymmetry then has to be broken in a way that this generic property of the supersymmetric theories is not lost. So break in a way that quadratic divergences do not reappear. in the quantum theory. One way of doing that is breaking symmetry spontaneously. There are other ways of doing that, breaking supersymmetry explicitly in a certain special way. We'll discuss them later. But first way of doing that is breaking them spontaneously. So spontaneously break, spontaneous breaking of SUSY does not introduce quadratic divergences. But what do we mean by spontaneous symmetry? We know what spontaneous symmetry breakings are. Spontaneous symmetry breakings are breakings where the Hamiltonian is symmetric, or Lagrangian density is symmetric, or action is symmetric, but the ground state of the theory is not. So ground state action is supersymmetric, but ground state of the theory is not. That's how we broke symmetry in the standard model. We broke the gauge symmetry here by having a ground state which is not symmetric. What does that mean? That means if I call ground state ket 0, then a supercharge acting on that will not be 0, and the conjugate supercharge acting on the ground state will not be 0. If they were 0, then ground state would be symmetric. So we also realized in supersymmetric theories potential function is always given in terms of the mod squares of all the f components of the chiral superfields you have. Sum square of mod square of those f terms, sum them up. That's what the potential in a generic supersymmetric theory is. And if you have gauge fields in the theory, then it's also square of the d term of the U1 gauge theory. And if you have a non-abelian gauge theory in your theory, the square gauge invariant square. So this is for U1 part, this is non-abelian. That is the generic form of the potential function in supersymmetric theory. And this is non-negative. If minimum of V is 0, because that's what we learned, that the minimum being 0 is the statement, is the value of vacuum expectation, value of potential in the ground state. And that being 0 is the statement that ground state respects C, which means in such a ground state, these operators are 0. This is what we learned in one of the earlier sessions, is that if the minimum of V is 0, V has a vacuum expectation value of 0, if V is 0, then ground state respects supersymmetry, because V can be written as, we have learned Hamiltonian can be written as square of supersymmetric charges, and that means Q on vacuum has to be 0 and Q bar on vacuum has to be 0. But if supersymmetry is broken by the ground states, then V cannot be 0. So spontaneous breaking would mean in fact positive, which can never be negative. Now, if ground state were supersymmetric, that means minimum was 0, that would mean, because this is sum of positive numbers, vacuum expectation value of each of the auxiliary fields has to be 0. So, this also implies F is 0, vacuum expectation value of V is 0, V is 0. But if it is broken spontaneously, what it means is that at least some of them are non-zero. All of them could be non-zero, or at least one of them is non-zero. Now, dA can never be non-zero, because if dA is non-zero, then you would at the same time break gauge symmetry. So, if you don't want to break gauge symmetry, for gauge symmetry to be exact, so then we are left with only possibilities is that some F is non-zero and some U1, the auxiliary field of the U1 supermultiplet is non-zero.
So this supercharged vacuum is not activated by the supercharger. Won't by choosing algebra it will imply that mu is also not eliminated.
Not P mu. Yeah, in general, they see, because if you take it the kinds of things, it's the P0 Hamiltonian. So, which means Hamiltonian, ground state Hamiltonian eigenvalue is non-zero. That's the beginning, right? Yes, 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 yes. Yes, you can choose some one of them to do it, but the square will have some of it there. Okay. So no, you keep the translation invariance, but the Hamiltonian will have non-zero. Some component of the supersymmetric charge will be non-zero. All right. Now, the one possibility, so the only possibility is that either some 1 or 2 or 3 x, whatever x you have, they have non-zero value, or the U1, the auxiliary field of the U1 supermultiplet has a non-zero expectation value. So there are therefore two mechanisms of spontaneous symmetry breaking. One is when some f's are 0, and other is when some d is non-zero, when some f is non-zero and some not. There are two such classes of models that you can build. Okay. So before I now give you examples of these two classes of models, there was one more nice conclusion of spontaneous symmetry breaking. When bosonic symmetries are broken, continuous bosonic symmetries are broken spontaneously, there is a theorem called Goldstone theorem that tells us that there is an associated massless particle for every generator of the bosonic symmetry that is broken, the Goldstone particle. Now that theorem is also valid for fermionic spontaneously broken fermionic charges. So Goldstone theorem. For spontaneously broken SUSY implies a massless fermion. Give it a name, Goldstino in the spectrum. Goldstone theorem was developed for bosonic symmetries, but it's true for all symmetries, both bosonic and fermionic. So now let me start with an example of the first type of supersymmetry breaking, F-type. There's a name given to this also, F-type or Orapati. I don't know how these guys write their names. Now in this model you need at least three chiral supermultiplets. So let's take them. Call the first component of the chiral superfield supermultiplet X. Second one, the fermionic partner of it is a complex scalar field. Fermionic partner we call it psi X, and the auxiliary field, a complex field of mass dimension 2, we call it Fx. And second one we call it Y, psi Y, and Fy. And third one we call it Z, psi Z, and Fz. So we start with a set of three chiral superfields or chiral supermultiplets. And then introduce a superpotential, some curly W, which is a holomorphic function of the scalar components of these multiplets. And then we realize, once you have done that, that these auxiliary fields are not independent fields. They are related to the superpotential, derivatives of superpotential. The constraint equations for Fx star was minus the superpotential x, y, z derivative with respect to x, and x, y star is minus and Fz star is minus derivative of superpotential with respect to z. Again some problem. And then in such a theory, potential function would be V of x, y and z and their complex conjugates would be mod square of curly w derivative which is x square which is same as fx square plus fy square plus fz square mod square. And like we said that this would be definitely positive or at worst 0, non-negative. I think I'll just go here. Exact supersymmetry would mean, I repeat, that vacuum expectation value of fx should be same as value expectation value of fy and all of them and fz, all three of them 0. Now for a given superpotential, it's always possible to imagine that there may be no solution which will simultaneously satisfy all these. Minimum of potential V which satisfies these objects, there will be no such solution. If that be so, then supersymmetry would be broken. It's possible can you imagine that there may be no simultaneous solution for the three equations fx equal to 0, fy equal to 0 and fz equal to 0. That would depend upon what superpotential we have chosen. Now I'll give you an example of a superpotential where this does happen. Consider a specific superpotential. Which is g times z y plus lambda x times z square minus m square. G is some coupling, dimensionful coupling of dimension mass. Lambda again some coupling, dimensionless coupling. M some parameter m square. This is some specific potential. And let's construct what are the possible auxiliary fields implied by the superpotential. So, what is Fx? Fx star is minus dw of dx. Take the variation with respect to x. That is minus lambda z square minus m square. Fy star, take the variation with respect to y, that is minus g times Z, and Fz star variation of this superpotential with respect to Z, that is minus Gy minus 2 lambda x Z. Is that right? I can't see from here. Is that correct? For this superpotential, these are the auxiliary fields as functions of the scalar fields. Now we ask the question, for supersymmetric ground state, the values of all these auxiliary fields has to be 0. Is there a solution for those three equations? Now, if I solve fx to be 0, that tells me z is m or plus minus m. Right? If I make this 0, that tells me z is z plus minus m, or what is it? 2. And if I solve this one, and for fy to be 0, I have z to be 0. Now these two are not mutually compatible. So fx and fy cannot be simultaneously 0. So there is no solution to this set fx equal to 0, fy equal to 0, and fz equal to 0. But then what is the ground state of the theory? Ground state is the one that minimizes the potential. So now what is the potential? Let me write down potential also here. Potential is fx mod square plus fy mod square plus fz mod square, and that is lambda square mod z square minus m square mod square plus g square z mod square plus gy plus 2 lambda x z mod square. So the ground state would be the minimum of this potential. And we have learned that these are all positive numbers, but the minimum of this positive number is z equal to m. Minimum of this positive number is z equal to 0, but that's not compatible. So that cannot be the minimum of the potential. So let me take the first two terms of the potential. Call it V1 is lambda z square m square mod square plus g square z square. The sum of two positive numbers. Let me minimize this separately and minimize the third term separately, and if the two are consistent. So that would be a way of doing minimum. I could do all three together, but this is a quicker way of doing it. I minimize these two together and minimize this. The minimum of this is when this is 0. This whole thing is 0. But the minimum of this object, these two objects, is what I would like to calculate. So how do I do that? Take the variation of V1 with respect to Z what do I get? There's a lambda square here, right? Is there a lambda square there? So lambda square z square, z star square m square times 2 z plus g square z star. That's the variation. Take the derivative with respect to z star. And equate these to 0 and find the solution. Now, instead of doing that, let me do this. Add this up. Something is not right. This should have been z here, right? And this is z star. This is with respect to it. Something is not right. Yeah, this is z, because this is z star derivative, this is z, yeah. There should be z and there should be z star. Variation of this with respect to z, mod square is this star times this, and derivative of that is 2z. So these two terms add up, 2 lambda square z star z times z star plus z. That is the first two terms. Second one is 2 lambda square m square. Is that what it is? Minus 2 lambda square plus g square. Sum again error? Huh? That will be? This will be z star. Huh? Why? This is the derivative of mod z square, that is z square minus m square times z star square minus m square. Yeah, that is the error I did first, right? Okay. So this is what it is. And now, if I do this object here, what happens is that this is minus, so I'll get a minus here, but this term will change sign. Is that right? This is minus becomes plus, so z star 1 is plus and z1 is minus, so this will become plus. So now, in order to find out minimum of the potential, we solve, put this equal to 0 and solve. At the same time, we minimize the last term of the potential. So the last term of the potential is gy plus 2 lambda xz equal to 0. Minimum of a square is when the object itself is 0. So we have to find now solution to this set of two equations. Now there are two cases here. case 1, when g square is greater than 2 lambda square m square. This g square is greater than this. If g square is greater than this, then with the minus sign also this is a positive quantity. With plus sign it's also a positive quantity, but even with the minus sign it's a positive quantity. Right? So this whole thing is a positive quantity because square, this is mod square, and this whole thing is a positive quantity. So this cannot be 0. So what we have is that this has to be 0. Is that clear? When g square is greater than this, then minus this times this is a positive quantity. So what is inside the bracket for the upper sign is positive. So that means z star plus z has to be 0. And for the lower sign, this is again a positive. So z star minus z has to be 0. So then solution is z plus minus z star is 0. That is z is 0. So the minimum the potential is when z is 0. So minimum of potential is when vacuum value of z is 0. And if vacuum value of z is 0, so is y. But there is no statement on x. X is undetermined. Which means for every value of x with z equal to 0 and y equal to 0, you have a ground state. So in the ground state, field x is 0, field y is 0, field z is 0, but x has any value. There is a technical name given to that. X is a flat direction of the potential. So if I were to draw up the potential, what it means is that I have potential which for every value of x, the bottom lies on the whole x line, real line, or with any value of x. Okay. So in particular now let me take x to be some real arbitrary number, vacuum value. And how, let me find out what is the spectrum of this theory now. How do I do that? I expand around the vacuum. So expand, write then x field to be A plus an xs. Expand x around the vacuum value, which is A, some constant, arbitrary constant. Arbitrary constant. Oh, we rubbed off the potential. But anyway, look at the notes. And put x equal to this, that is lambda square z minus m square mod square plus g square z square plus mod gy plus 2 lambda xs plus a z mod square. That's what the potential is around that vacuum now. Vacuum x equal to a, z equal to 0 and y equal to 0. Expand this out and write down the bilinear terms. Bilinear. If you write the bilinear terms, that will give you the mass terms of the various fields. Because mass terms in a potential are the bilinear fields, and other trilinear or quadratic those will give you the couplings. So let's identify the mass terms. Bilinear terms, that is mass terms. Have I done that somewhere? Well, that's so. From this, you have lambda square times m square minus z square plus z star square. Open this up, you have a bilinear term this. Bilinear term, this is square of this, that is z to the 4, that's a higher order. It's the cross term that you will get it. M times z square and m times z star square. And is there a factor of 2 somewhere? No, this is what is now. Okay? Then this term is as it is. But there is a term z mod z from here also, a 2 lambda a times z mod square. So 4 lambda square a square mod z square. Then there is also this term g square y mod y star, or let me call this z star explicitly, square of this. Then there is also a term which is mixed term of y and z, which is 2 lambda a g times y z star plus y star z. And then there are other higher order terms, more than 2 fields. So these bilinear terms give us the masses of the fields. Now clearly these bilinear terms are not in a diagonal form in which we can identify masses of the particles. So this mass matrix is not diagonal. So you may diagonalize it. But let me write in the matrix form now. So if I write this as half x y star y z star z times the mass matrix mb square times y star z z. So if I write in the basis of y star z and z star, this is a 4 cross 4 matrix. what is the structure of this matrix? Y entry is Y star, Z star, Y star, Y, Z star, Z. So let me read the Y star piece, that is this entry, G square. Y star is, there is none. YZ star is here. Y star Z is here. 2 lambda A G. Y star Z star is there. Similarly now, G square 0 2 lambda A G. This is Y star, that is G, and Y Z star, that is this. Notice in this way of doing that, we have gotten two terms, G square Y star Y and G Y square Y. So that's twice the number that we have here, because there is only one. So that's why this normalization half here. Now from Z star Y is here. This is 2 lambda A G. Z star Y star, there is no term, and Z star is G square 4 A square lambda square, and this is twice lambda square M square. Look at Z star term is minus twice lambda square, but here is only no factor of 2. That is again taken care of this by this half. Now the last one is ZY term, there is none. 2G lambda A 2 lambda square M square G square 4 lambda square A square. That's the mass matrix. In the notes, I think I gave it to you earlier. I think there are some errors in this, but this is now the correct one. I think there is perhaps 2 missing here or lambda square missing here in this term and this term. So we have the mass matrix. Now we may diagonalize it and to find out what are the eigenvalues, and those would be eigenmasses of the various scalar fields of this theory, bosonic fields. But before we do that, there is something we notice already. There is no x square piece here, xs square. No xs mod square piece in the potential. Therefore, mass of xs is 0. Now you may, like I said, diagonalize it and find out what is the spectrum, but I am not interested in diagonalizing it because that's not going to be illuminating. But what is interesting is I can find out what is the sum of the diagonal eigenvalues, which is the trace of this matrix, which is the sum of the masses of the scalar fields. So the trace and what is the trace? G square plus 8 times lambda square A square. So the sum of the Bose eigenvalues of the mass matrix, bosonic mass matrix, is this object. So now, what about the fermion masses? So remember from your Lagrangian density, how would the fermion masses emerge? There will be a term, they would be given by bilinear in fermions, psi I. Psi I is shorthand for psi x, psi y, and psi z. Would be given by psi I minus half psi j times the superpotential derivative with respect to phi I and phi j, where now we are using for phi I is x, y, z. That's how the fermionic bilinears would appear in the Lagrangian density plus complex conjugates. This is how we had constructed the F term of the superpotential is the Lagrangian part of the Lagrangian density, and F term has this piece which has fermion bilinears. Now you evaluate this at the minimum of the potential. That would give you the mass matrix of fermions. Minimum of the potential is x equal to a, y equal to 0, and z equal to 0. Now that is same as 1/2 psi I psi j, but this object is d of d phi I of because Fj is the first derivative of the superpotential. And you evaluate it at x equal to a, y equal to 0, z equal to 0. And f I is the shorthand for fx, fy, and fz. So now I know what fx's are, so therefore I know how to evaluate the fermion mass matrix. I think I have not written there, I rubbed it off. So let me write what was fx? Fx was minus lambda z square minus m square. Fy was minus g star. It was minus gz, and fz star was minus gy plus twice lambda xz. So let me take d dx of fx star, fy star, fz star. What do I get? 0, 0, 0 at x equal to a, y equal to 0, z equal to 0. The only this is 0, this is 0. Only piece I get here is from here, that is 2 lambda z, but at z equal to 0, that's 0. There is no y in this, so 0. There is no y here. There is one y here, so that gives me g. Minus g, but this is a minus here. Now z, there is a z here. That gives me 2 lambda times z, but at z equal to 0, that is 0. This gives me g. Derivative with respect to z is g minus g, but I have a minus there, so g. Derivative with respect to z here is minus 2 lambda x, and x at value a is 2 lambda a. So for fermion matrix ij component, which is minus dfi star by d phi j, evaluated at x equal to a, y equal to 0, z equal to 0. Let me draw a matrix for it. Psi x, psi y, psi z, psi x, psi y, psi z. 0, 0, 0, 0, 0, g, 0, g, 2 lambda a. Is lambda a without g, right? Yes. So that's my mass matrix. Let me calculate the square of the mass matrix. I think there are some errors in the notes for this also, but this is right. The square of this is 0, this times this is 0, this times this is g square, this times this is 2 lambda ag, then this times this is 2 lambda ag, and this times this is g square plus 4 lambda a square. So now let's take the trace of this matrix. What's the trace? G square plus 2g square plus 4 lambda square a square. Is that what it is? Okay. Anyway, before I make any more remarks about the trace, notice something.
this matrix has 1, 0 eigenvalue. So if you say eigenvalues 0, and if you diagonalize this, I think this, it is g square plus twice lambda square a square plus minus square root of plus minus 2 lambda a square root of g square plus lambda square a square. So point is, important point to note is that it has 1 0 eigenvalue and 2 non-zero eigenvalues. Zero eigenvalue corresponds to the mass of psi x. So mass of psi x is 0. Psi x is the fermion in the multiplet in which Fx is. Fx is the auxiliary field that picked up non-zero vacuum expectation value. So the psi x is in the multiplet in which the auxiliary field has picked up a non-zero exponent. So this is the Goldstein. So psi x is the Goldstein. Now, getting back to trace, this is mf square, right? Now, the two traces have an interesting relationship. We have in this theory here, we have written this as a 4 cross 4 matrix, but we in complex fields, but in terms of real fields, it's a y and y star are each other's stars. So we have only 2 complex fields in fact. So what we have is 2 complex fields or 4 real scalar fields. So the masses of those 4 scalar real fields are given by this mass matrix. In addition to that, we have set of 2 real fields in Sx which are massless. So this is our set of scalar fields. So that is the trace of the mass matrix is of all these real 6 fields. But fermion mass matrix is for set of 3 fermions. This one massless, these 2 have. But each fermion is 2 degrees of freedom. So the set of independent real fields here we have is 2. And each one of them has the same mass here, here. So this essentially factor 2 is just counting that number. So we rewrite this formula in the following way. Super trace of mass matrix, and super trace of mass matrix is trace of the boson, trace minus 1 to the j. J is the spin. For bosons, spin 0. For fermions, spin half, so 2j. Put a minus sign there. Times 2j plus 1, which counts the components in the representation. For scalar, it's 1. For every scalar, it's 1. For every fermion, it's 2 times which is m boson mass square minus twice m fermion mass square trace is 0. This is a compact way of writing the same formula that we wrote earlier here. The trace of bosonic mass square matrix is twice the trace of fermionic mass. And compactly you write it like this. This is a generic property of supersymmetric theories. The sum of the bosonic mass squares is equal to sum of the fermionic mass squares of this type of supersymmetric breaking. So this was the first case of we had studied of the various relationships of the coupling constants. So let me go back to the potential now. Case 2. Recall the conditions for minimizing potential that we had were 2 lambda square z bar plus g square plus minus 2 lambda square m square times z star plus minus z is 0 and gy plus 2 lambda xz is 0. These were the conditions for minimum potential that we had worked out. Now the case 2 is now when g square is less than 2 lambda square m square. Now if g square is less than lambda square, for the upper sign, this object becomes negative. For lower sign, it's still positive, but upper sign it becomes negative. So then the minimum will correspond to this object for the upper sign to be 0, which means minimum of the potential is 2 lambda square zz square equal to 2 lambda m square minus g square. From the upper sign. That is for the minimum. For the lower sign, this is a positive object. The minimum is when z star minus z is 0. Is that clear? For the upper sign, because this object is negative, so this minus this can be 0. That gives you this condition. For the lower sign, this side is positive. The only way you can get this minimum is if this is minimum. Z minus z star minus z is minimum. And then this has to be 0. Now what is the solution here? Is from here, this tells me z is real, z star is z. So minimum of z is square root of m square minus g square 2 lambda square. and minimum of y from here is 2 lambda by g minimum of x z the ground state of x and z, and z and z ground state is this much and x is left undetermined. Now what happens to put auxiliary fields? Fx ground value, Fx was lambda z square minus m square. Is that what it was? Z star square m square vacuum expectation value. This is what Fx was, just from your notes if you see it, is lambda times z square minus m square. F star, that was this. But z and z star is same at the ground state. So this object is equal to minus lambda z square minus m square is g square by 2 lambda square minus, so they will become plus. So that is what is the Fy? Fy was, what was Fy? Have I written it somewhere? Oh, Fy is g times z. That's what Fy was. So g times vacuum value for F, and that is minus g times square root of m square minus g square 2 lambda square. And Fz that's exactly this. So in the ground state now we have is that Fx vacuum expectation value is non-zero, and this is g square by 2 lambda. Fy vacuum expectation value is non-zero, and that is minus g by square root m square minus g square by 2 lambda, and vacuum value of Fz is 0. Fz is this relation. We had minimized Fz by putting it Fz was 0, right? So that's what this condition is. So we have, in this case now, the second case, Fx picks up a non-zero vacuum expectation value, Fy picks up a non-zero expectation value by this much amount. But I can always construct a linear combination of Fx and Fy whose vacuum expectation value will be still 0. One linear combination of Fx and Fy still has vacuum expectation value 0. So, we can write that as Fx sine alpha plus Fy cosine alpha is 0, and if you work it out, then tangent alpha is 2 lambda m square minus g square by 2 lambda square by g. So, this linear combination of Fx and Fy still has 0 vacuum expectation value, but the orthogonal combination So, what we did was that we found out what is the vacuum values for Fx and Fy and Fz. Vacuum expectation value of Fx and Fy are these, but I can construct a new field which is a linear combination of these two objects in a way that its vacuum expectation value is 0. That linear combination is this times sine alpha, that times cosine alpha, where now alpha is given by tangent alpha, because this will make this identically 0. Because Fx vacuum expectation value is this. So, a superfield which is say auxiliary field which is Fx sine alpha plus Fy cosine alpha, this auxiliary field has a 0 expectation value, but its orthogonal combination Fx cosine alpha plus Fy sine alpha has a vacuum expectation value, non-zero, has vacuum expectation value 0. So, if I make a linear superfield, a linear combination of these two superfields, the x-type superfield and y-type superfield, which means the scalar components would be x times sine alpha plus y times cosine alpha, auxiliary fields are fx times this, and fermion components will be psi x sine alpha plus psi y cosine alpha, and the orthogonal combinations. These are new superfields, and in these new superfields, the one corresponding to here has an auxiliary field whose vacuum expectation value is 0, and this one whose vacuum expectation value is non-zero. Clear? So, therefore, if I had to identify Goldstone boson, where will it be? Goldstino, not boson boson, Goldstone fermion. It will be in the combination which has picked up a non-zero expectation value. So, therefore, Goldstino is minus psi x cosine alpha plus psi y sine alpha. So, if I were to work out the mass matrix of this theory, I would find that this combination of fermions will be massless. Massless. Now you could do the exercise and work out the mass matrices, bosonic mass matrix and fermionic mass matrix in this theory by expanding around the grounds, various fields, scalar fields around the ground state. And that I think I'll leave as an exercise. Check trace of the bosonic mass matrix square is twice the trace of fermionic mass matrix. Now what we did explicitly in the first case, just check that it's so for this case also. I think I'll stop there today. Anything? What's it?